ಶುರು ಮಾಡೋದು ಸರ್.
Yes, sir.
ಸೊ ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರಗಳು. ಗುಡ್ ಈವ್ನಿಂಗ್ ಒನ್ ಅಂಡ್ ಆಲ್. ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾ ಶೋಧ ಯೋಜನೆಯ ಇಂದಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಡಾಕ್ಟರ್ ಚಂದ್ರಶೇಖರ್ ಶೆಟ್ಟಿ ರವರು ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ಅವರನ್ನು ಈ ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾ ಶೋಧನೆಯ 69ನೇ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತಿಸ್ತಾ ಇದ್ದೀನಿ. ಐ ವೆಲ್ಕಮ್ ಟು ಯು ಸರ್. ಸೊ ಅದೇ ರೀತಿ ಇಂದಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಹಾಜರಾಗಿರುವಂತಹ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿ ಮಿತ್ರರು, ಅಧ್ಯಾಪಕರು, ಶಿಕ್ಷಕರು ಹಾಗೂ ನನ್ನ ಸಹೋದ್ಯೋಗಿಗಳನ್ನು ಕೂಡ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಸ್ವಾಗತಿಸುತ್ತಿದ್ದೇನೆ. ಸೊ ನಾವು ಚಂದ್ರಶೇಖರ್ ಶೆಟ್ಟಿ ಸರ್ ಬಗ್ಗೆ ಹಲವಾರು ತರಗತಿಗಳಲ್ಲಿ ಅವರ ಒಂದು ಕಿರುಪರಿಚಯವನ್ನು ಮಾಡಿಕೊಟ್ಟಿದ್ದು, ಸೊ ಸಮಯಾವಕಾಶವು ಕಡಿಮೆ ಇರುವ ಕಾರಣ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮಕ್ಕೆ ಅವರನ್ನು ನೇರವಾಗಿ ಈ ಒಂದು ವೇದಿಕೆಗೆ ಮತ್ತೊಮ್ಮೆ ಸ್ವಾಗತಿಸುತ್ತಾ, ಓವರ್ ಟು ಯು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು. ಪ್ರಥಮವಾಗಿ ವಿದ್ಯಾರ್ಥಿ ಪ್ರತಿಭಾ ಶೋಧನಾ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಮಾಡಿಕೊಡಲು ಅವಕಾಶ ಮಾಡಿಕೊಟ್ಟ KSTಯ ಎಲ್ಲ ಪದಾಧಿಕಾರಿಗಳಿಗೆ ನನ್ನ ವಂದನೆಗಳು. ಅದೇ ರೀತಿ ಇವತ್ತಿನ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಆನ್ಲೈನ್ ಭಾಗವಹಿಸುವಂತ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೂ ನನ್ನ ಶುಭಾಶಯಗಳು. ಇವತ್ತು ನಾನು ಸೆಕೆಂಡ್ PUCಯಲ್ಲಿ ಪಾಠ ಮಾಡುವಂತಹ ಒಂದು ಬಹುಮುಖ್ಯ ಟಾಪಿಕ್ ಕರೆಂಟ್ ಎಲೆಕ್ಟ್ರಿಸಿಟಿಯ ಬಗ್ಗೆ 1 ಗಂಟೆಗಳ ಕಾಲ ತಮ್ಮ ಜೊತೆ ಮಾತುಕತೆ ಮಾಡ್ತಾ ಇದ್ದೇನೆ. ಆದಷ್ಟು ನಾನು ಕನ್ನಡದಲ್ಲಿ ಮಾತಾಡಲಿಕ್ಕೆ ಪ್ರಯತ್ನ ಮಾಡುತ್ತೇನೆ ಪ್ರತಿ ಉಪನ್ಯಾಸದಂತೆ. ಇವತ್ತು ಕೂಡ ಅಂತಹ ಒಂದು ಪ್ರಯತ್ನದಲ್ಲಿ ನಾನು ಮುಂದುವರಿಯುತ್ತೇನೆ. ಕರೆಂಟ್ ಎಲೆಕ್ಟ್ರಿಸಿಟಿ ಅಂದ್ರೆ ನಾವು ಪ್ರತಿಯೊಬ್ಬರೂ ನಮ್ಮ ದಿನನಿತ್ಯ ಬಳಕೆ ಮಾಡುವಂತಹ ಒಂದು ವಿಷಯ. ಇಲ್ಲಿ ನಾವು AC ಕರೆಂಟ್ ಅನ್ನು ಬಹಳ ಮುಖ್ಯವಾಗಿ ಉಪಯೋಗಿಸ್ತೇವೆ ಎಲೆಕ್ಟ್ರಿಕಲ್ ಇಕ್ವಿಪ್ಮೆಂಟ್ಸ್ಗೆ. ಅದೇ ರೀತಿ ಬ್ಯಾಟ್ರಿಯ ಮೂಲಕ DC ಕರೆಂಟ್ ಅನ್ನು ಉಪಯೋಗಿಸ್ತೇವೆ. ಆದರೆ ಈ ಅಧ್ಯಾಯದಲ್ಲಿ ನಾವು AC ಅಥವಾ DC ಅಂತ ಸಪರೇಟ್ ಆಗಿ ನೋಡದೆ ಕರೆಂಟ್ ಎಲೆಕ್ಟ್ರಿಸಿಟಿ ಅಂದ್ರೆ ಏನು, ಮತ್ತೆ ಮುಖ್ಯವಾಗಿ ನಾವು DC ಮನದಲ್ಲಿಟ್ಟುಕೊಂಡು ಡೈರೆಕ್ಟ್ ಕರೆಂಟ್ ಅನ್ನು ಮನಸ್ಸಿನಲ್ಲಿಟ್ಟುಕೊಂಡು ಈ ಪಾಠವನ್ನು ಮಾಡ್ತೇವೆ. ನಮ್ಗೆಲ್ಲ ತಿಳಿದಿರುವಂತೆ ಕರೆಂಟ್ ಅಂದ್ರೆ ಯಾವುದೇ ವಸ್ತು ಒಂದು ಫ್ಲೋ ಆಗುವ ವಸ್ತುವಿಗೆ ಕರೆಂಟ್ ಅಂತ ಹೇಳ್ತೇವೆ. ನೀರಿನ ಫ್ಲೋಗೆ ಕರೆಂಟ್, ಅಥವಾ ಒಂದು ದೊಡ್ಡ ಜನಸಂಖ್ಯೆ ಮೂವ್ ಆಗ್ತಾ ಇದೆ ಒಂದು ಕಡೆ, ಕರೆಂಟ್ ಫ್ಲೋಯಿಂಗ್. ನಮ್ಮ ಈ ಟಾಪಿಕ್ ಅಲ್ಲಿ ಕರೆಂಟ್ ಎಂಬುದು ಸ್ಪೆಸಿಫಿಕ್ ಆಗಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಚಾರ್ಜಸ್ಗಳ ಮೂವ್ಮೆಂಟ್ ಅನ್ನು ಸೂಚಿಸುತ್ತದೆ. ವಾಟ್ ಯು ಮೀನ್ ಬೈ ಕರೆಂಟ್? ಈಗ ನಾವು ಕರೆಂಟ್ ಅನ್ನು ಡಿಫೈನ್ ಮಾಡ್ಲಿಕ್ಕೆ ಹೊರಟ್ರೆ, ಈಗ ನೆಟ್ ಅಮೌಂಟ್ ಆಫ್ ಚಾರ್ಜ್ ಫ್ಲೋಯಿಂಗ್ ಅಕ್ರಾಸ್ ದ ಏರಿಯಾ ಇನ್ ಎ ಫಾರ್ವರ್ಡ್ ಡೈರೆಕ್ಷನ್ ಇನ್ ದ ಟೈಮ್ ಇಂಟರ್ವಲ್ ಆಫ್ ಟಿ. ಒಂದು ಯಾವುದೇ ಒಂದು ವೈರ್, ಕಂಡಕ್ಟಿಂಗ್ ವೈರ್ ಇದ್ರೆ ಅದರಲ್ಲಿ ನಾವು ಕರೆಂಟ್ ಅನ್ನು ಹರಿಸಿದ್ರೆ ಆಗ ನಮ್ಗೆ ಗೊತ್ತಿದೆ, ನಮ್ಗೆ ಅಲ್ಲಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಚಾರ್ಜಸ್ ಇದ್ರೆ ಅದು ಸ್ಟಡಿ ಆಗಿರ್ತದೆ. ಸ್ಟಡಿ ಅಂದ್ರೆ ಯಾವುದೇ ಕಡೆಗೆ ಹೋಗ್ತಾ ಇರುವುದಿಲ್ಲ, ಅಲ್ಲಿ ಸ್ಥಿರವಾಗಿರುತ್ತದೆ. ಆದ್ರೆ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಅನ್ನು ಅಪ್ಲೈ ಮಾಡುವುದು ಅಥವಾ ಪೊಟೆನ್ಷಿಯಲ್ ಡಿಫರೆನ್ಸ್ ಅನ್ನು ಕ್ರಿಯೇಟ್ ಮಾಡುವುದರ ಮೂಲಕ ನಾವು ಒಂದು ಕಡೆಯಿಂದ ಇನ್ನೊಂದು ಕಡೆಗೆ ಎಲೆಕ್ಟ್ರಿಕ್ ಚಾರ್ಜಸ್ ಅನ್ನು ಮೂವ್ ಮಾಡಲಿಕ್ಕೆ ಸಾಧ್ಯ ಆಗ್ತದೆ. ಆಗ ಎಷ್ಟು ಚಾರ್ಜ್ಗಳು ಮೂವ್ ಆಗ್ತವೆ ಅದರ ಮೇಲೆ ನಾವು ಯಾವ ರೀತಿಯ ಕರೆಂಟ್ ಇದೆ, ಎಷ್ಟು ಕರೆಂಟ್ ಇದೆ ಎಂದು ತಿಳಿಸ್ತೇವೆ. ಕ್ರಾಸ್ ಸೆಕ್ಷನಲ್ ಏರಿಯಾ ಅಂತ ನಾವು ಯಾಕೆ ತೆಕ್ಕೊಳ್ತೇವೆ ಅಂತ ಹೇಳಿದ್ರೆ, ಅದು ನಮಗೆ ಒಂದು ಆ ವೈರ್ನ ಎಷ್ಟು ದಪ್ಪ ಇದೆ, ಎಷ್ಟು ದಪ್ಪದ ವೈರ್ ಅಂತ ಐಡಿಯಾ ಕೊಡ್ತದೆ. ಅದ ಕಾರಣ ಟೋಟಲ್ ಯಾವುದೇ ಒಂದು ವೈರ್ ಇದ್ರೆ ನಾನು ನಿಮಗೆ ನೆಕ್ಸ್ಟ್ ಚಿತ್ರದಲ್ಲಿ ತೋರಿಸ್ತೇನೆ. ಒಂದು ವೈರ್ ಈ ರೀತಿ ಇದ್ರೆ, ಒಂದು ವೇಳೆ ಒಂದು ವೈರ್ ಈ ರೀತಿ ಇದ್ರೆ, ಈ ರೀತಿ ಒಂದು ವೈರ್ ಇದ್ರೆ, ಇಲ್ಲಿ ನಾವು ಎಲ್ಲ ಪ್ಲಸ್ ಚಾರ್ಜಸ್ ಅಥವಾ ಮೈನಸ್ ಚಾರ್ಜಸ್ ಇದ್ರೆ, ಈಗ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಅನ್ನು ಅಪ್ಲೈ ಮಾಡಿದ್ರೆ ಎಲ್ಲವೂ ಆ ಕಡೆ ಈ ಕಡೆಗೆ ಫ್ಲೋ ಆಗ್ತಾ ಇರ್ತವೆ ಯಾವಾಗ ನಾವು ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಅನ್ನು ಅಪ್ಲೈ ಮಾಡದಿರುವಾಗ. ಅದಕ್ಕೆ ನೆಟ್ ಫ್ಲೋ, ಯಾವುದೇ ಒಂದು ಪರ್ಟಿಕ್ಯುಲರ್ ಏರಿಯಾವನ್ನು ತಗೊಂಡು ಈ ಜಾಗವನ್ನು ತಗೊಂಡ್ರೆ, ಸರ್ಫೇಸ್ ಏರಿಯಾವನ್ನು ತಗೊಂಡ್ರೆ ಇಲ್ಲಿ ಎಷ್ಟು ಚಾರ್ಜ್ಗಳು ಆ ಕಡೆ ಈ ಕಡೆಗೆ ಹೋಗ್ತಾ ಇದ್ದಾವೆ ಅಂತ ಪರ್ ಸೆಕೆಂಡ್ಗೆ ನೋಡ್ಬೇಕು. ಒಂದು ಗಿವನ್ ಟೈಮ್ ಇಂಟರ್ವಲ್ ತಗೊಂಡ್ರೆ ಸ್ಟಡಿ ಕರೆಂಟ್ ಅಂದ್ರೆ ಈ ರೀತಿ ಟೋಟಲ್ ಚಾರ್ಜಸ್ ಮೂವಿಂಗ್ ಐದರ್ ಸೈಡ್. ಅಂದ್ರೆ ಒಂದು ಕಡೆ ಹೋದದ್ದು ಒಂದು ಟೈಪ್ ಚಾರ್ಜಸ್ ಇರ್ತದೆ, ಇನ್ನೊಂದು ಕಡೆ ಇನ್ನೊಂದು ಟೈಪ್ ಚಾರ್ಜಸ್ ಇರ್ತದೆ. ನೆಟ್ ಚಾರ್ಜ್ ಅಂತ ಏನು ಹೇಳಿದ್ರೆ ಅಂದ್ರೆ ಟೋಟಲ್ ಚಾರ್ಜಸ್ ಡಿವೈಡ್ ಬೈ ಟಿ ಟೈಮ್ ಇಂಟರ್ವಲ್. ಆದ್ರೆ ನಮ್ಗೇನು ಗೊತ್ತಿರಬೇಕು ಅಂತ ಹೇಳಿದ್ರೆ, ಯಾವುದೇ ಒಂದು ವೈರ್ ಅಥವಾ ಸಿಸ್ಟಮ್ ಅಲ್ಲಿ ಸ್ಟಡಿ ಚಾರ್ಜಸ್ ಇರೋದು ಬಹಳ ಕಷ್ಟ. ಇನ್ ಜನರಲ್ ನಾವು ಹೇಳ್ತೇವೆ ಸ್ಟಡಿ ಚಾರ್ಜಸ್ ಇರುವುದಿಲ್ಲ, ಇನ್ಸ್ಟಂಟೇನಿಯಸ್ ಚಾರ್ಜಸ್. ಯಾಕಂದ್ರೆ ಒಂದೇ ರೀತಿಯ ಚಾರ್ಜಸ್ ಫ್ಲೋ ಆಗ್ತಾನೆ ಇರುವುದಿಲ್ಲ ಯಾವಾಗಲೂ. ಕಾರಣ ಇನ್ ಜನರಲ್ ದ ಕರೆಂಟ್ ಅಟ್ ಎ ಟೈಮ್ ಟಿ across the cross section of a conductor is defined as the value of the ratio of dq or delta q to delta t in a time interval of delta t which is tending to 0. ಇದೊಂದು ನಾವು ಲಿಮಿಟೇಷನ್ ಮ್ಯಾಥಮೆಟಿಕಲ್ ಆಗಿ ನಾವು ಇದನ್ನು ಬರಲಿಕ್ಕೆ ಹೊರಟ್ರೆ ಐ ಆಫ್ ಟಿ ಅಂದ್ರೆ ಕರೆಂಟ್ ಇನ್ ಎ ಟೈಮ್ ಇಂಟರ್ವಲ್ ಆಫ್ ಟಿ ಈಸ್ ಡೆಲ್ಟಾ ಕ್ಯೂ ಬೈ ಡೆಲ್ಟಾ ಟಿ. ಡೆಲ್ಟಾ ಕ್ಯೂ ಏನು ಡೆಲ್ಟಾ ನಿಮಗೆ ಗೊತ್ತಿದೆ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಅಲ್ಲಿ, ಡೆಲ್ಟಾ ಕ್ಯೂ ಅಂದ್ರೆ ಬಹಳ ಸಣ್ಣ ಅಂತ ಅರ್ಥ. ಯಾವುದೇ ಸಣ್ಣ ಅಮೌಂಟ್ ಇದ್ದು ಚಾರ್ಜು ಅದೇ ಅತ್ಯಂತ ಸಣ್ಣ ಅಮೌಂಟ್ ಇದ್ದು ಟೈಮ್ ಅಂದ್ರೆ ಟೈಮ್ ಸೊನ್ನೆಯೂ ಆಗಿರ್ಬೋದು, ಆ ಟೈಮಲ್ಲಿ ಅಕ್ರಾಸ್ ಗಿವನ್ ಏರಿಯಾ ಪಾಸ್ ಆಗುವಂತಹ ಚಾರ್ಜಸ್ಗಳು ಆ ಕರೆಂಟ್ ಅನ್ನು ನಿರ್ಧರಿಸ್ತವೆ. ಐ ಆಫ್ ಟಿ ಇಸ್ ಈಕ್ವಲ್ ಟು ಲಿಮಿಟ್ ಡೆಲ್ಟಾ ಟಿ ಈಸ್ ಟೆಂಡಿಂಗ್ ಟು 0 ಡೆಲ್ಟಾ ಕ್ಯೂ ಬೈ ಡೆಲ್ಟಾ ಟಿ. ಯಾಕೆ ಅಂತ ಹೇಳ್ತೇವೆ ಅಂದ್ರೆ ಇನ್ಸ್ಟಂಟೇನಿಯಸ್ ದಟ್ ಮೊಮೆಂಟ್ ಆಫ್ ಟೈಮ್ ವಿದಿನ್ ವೆರಿ ಶಾರ್ಟ್ ಡ್ಯೂರೇಷನ್ ಆಫ್ ಟೈಮ್ ಎಷ್ಟು ಚಾರ್ಜಸ್ ಒಂದು ಕಡೆಯಿಂದ ಕಡೆಗೆ ಹೋಗ್ತವೆ ಅದರ ಮೇಲೆ ನಾವು ಕರೆಂಟ್ ಅನ್ನು ಡಿಫೈನ್ ಮಾಡಬೇಕಾಗ್ತದೆ. ದಿಸ್ ಇಸ್ ದ ಡೆಫಿನಿಷನ್ ಆಫ್ ದ ಎಲೆಕ್ಟ್ರಿಕ್ ಕರೆಂಟ್. ಹಿಯರ್ ಡೆಲ್ಟಾ ಕ್ಯೂ ಬಿ ದ ನೆಟ್ ಚಾರ್ಜ್ flowing across the section. ಅದೇ ರೀತಿ ಡೆಲ್ಟಾ ಟಿ is the time interval. This you try to understand. This will talk about the instantaneous current. ಅಂದ್ರೆ ಈಗ ನಾವು ಸ್ಟಡಿ ಕರೆಂಟ್ ಅನ್ನು ಬಿಟ್ಟು ಬಹಳ ವೇಗವಾಗಿ ಕೂಡ ಒಂದು ಚಾರ್ಜಸ್ ಒಂದು ಕಡೆಯಿಂದ ಇನ್ನೊಂದು ಕಡೆಗೆ ಮೂವ್ ಅಂದ್ರೆ ಅದು ಒಂದು ಕರೆಂಟ್ಗೆ ಕಾರಣ ಆಗ್ತದೆ ಅಂತ ತಿಳ್ಕೊಳ್ಬೇಕಾಗ್ತದೆ. ಈಗ ನೋಡಿ, ಎಲೆಕ್ಟ್ರಿಕ್ ಕರೆಂಟ್ ಬೇಕಿದ್ರೆ ನಮಗೆ ಒಂದು ಕಂಡಕ್ಟರ್ಗಳು ಬೇಕು. ಕಂಡಕ್ಟರ್ ಅಂದ್ರೆ ಏನು ನಮಗೆಲ್ಲ ಗೊತ್ತಿದೆ. ವಿ ಡಿಫೈನ್ ಥಿಂಗ್ಸ್ ಇಂಟು 3 categories: good conductors of electricity, bad conductors of electricity, and semiconductors. When I say good conductors of electricity, all the metallic wires are good conductors of electricity. ಅದು ಅಲ್ಯೂಮಿನಿಯಂ ಇರ್ಬೋದು, ಕಾಪರ್ ಇರ್ಬೋದು, ಅಥವಾ ಟಂಗ್ಸ್ಟನ್ ಇರ್ಬೋದು, ಎಲ್ಲ ಗುಡ್ ಕಂಡಕ್ಟರ್ಸ್. ಇವನ್ ಸಿಲ್ವರ್ ಇಸ್ ಆಲ್ಸೋ ಪಾಸಿಬಲ್, ಬೆಳ್ಳಿಗೂ ಇರ್ತದೆ. ಬ್ಯಾಡ್ ಕಂಡಕ್ಟರ್ಸ್ ನಿಮ್ಗೆ ಗೊತ್ತಿದೆ, ಈ ರಬ್ಬರ್, ಮರ ಇವೆಲ್ಲ ಅಥವಾ ಯಾವುದೇ ಪಾಲಿಮರ್ಗಳೆಲ್ಲ ಬ್ಯಾಡ್ ಕಂಡಕ್ಟರ್ಗಳಿರ್ತವೆ. ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ ನಾವು ಕಲ್ತಿದ್ದೇವೆ, ಅದು ಸಿಲಿಕಾನ್, ಜರ್ಮೇನಿ ಅಥವಾ ಗ್ಯಾಲಿಯಂ ನೈಟ್ರೇಟ್, ಗ್ಯಾಲಿಯಂ ಆರ್ಸೆನೈಡ್ ಅಂತ ಕಾಂಪೌಂಡ್ ವಸ್ತುಗಳು, ಇವೆಲ್ಲ ಕಂಡಕ್ಟರ್ಸ್ಗಳು ಅಂದ್ರೆ ಸೆಮಿಕಂಡಕ್ಟರ್ಸ್ಗಳು. ನಾವು ಈ ಅಧ್ಯಾಯದಲ್ಲಿ ಅಭ್ಯಾಸ ಮಾಡುವಂತಹ ವಿಷಯ ಅಂದ್ರೆ ಅದು ಗುಡ್ ಕಂಡಕ್ಟರ್ಸ್ಗಳಲ್ಲಿ ಎಲೆಕ್ಟ್ರಿಕ್ ಕರೆಂಟ್ ಪಾಸ್ ಆಗುವ ವಿಧಾನಗಳು ಮಾತ್ರ. ಆದರೆ ಕೆಲವು ಅದರ ಪ್ರಾಪರ್ಟಿಗಳನ್ನು ನಾವು ಸ್ಟಡಿ ಮಾಡ್ತೇವೆ. ಈ ಚಿತ್ರದಲ್ಲಿ ನೀವು ನೋಡ್ಬೋದು, ಒಂದು ಎಂಡ್ ಅದು ವೈರು, ಒಂದು ಎಂಡಲ್ಲಿ ಪ್ಲಸ್ ಚಾರ್ಜ್ ಇದೆ ಕ್ಯೂ, ಇನ್ನೊಂದು ತುದಿಯಲ್ಲಿ ಮೈನಸ್ ಕ್ಯೂ ಇದೆ. ಈಗ ಒಂದು ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್ ಅನ್ನು ಅಪ್ಲೈ ಮಾಡಿದ್ದಾರೆ. ಯು ಕ್ಯಾನ್ ಸಿ ಇನ್ ದ ಮಿಡಲ್ ಇ ಎಲೆಕ್ಟ್ರಿಕ್ ಫೀಲ್ಡ್. ಇನ್ ಸಚ್ ಕೇಸಸ್ ದೇರ್ ಇಸ್ ಎ ಫ್ಲೋ ಆಫ್ ಚಾರ್ಜಸ್ ಫ್ರಮ್ ಮೈನಸ್ ಕ್ಯೂ ಟು ಪ್ಲಸ್ ಕ್ಯೂ. ಮೈನಸ್ ಕ್ಯೂ ಎಂಡಿಂದ ಪ್ಲಸ್ ಕ್ಯೂ ಎಂಡಿಗೆ ಚಾರ್ಜ್ಗಳು ಪ್ರವಹಿಸ್ತವೆ. ದಿಸ್ ವಿಲ್ ಕಾನ್ಸ್ಟಿಟ್ಯೂಟ್ ಎ ಕರೆಂಟ್. ಈಗ ಯಾವ ಪ್ರಮಾಣದ ಕರೆಂಟ್ ಇದೆ ಇದನ್ನು ನಾವು ಅಧ್ಯಯನ ಮಾಡಲಿಕ್ಕೆ ಪ್ರಸಿದ್ಧ ಸೈಮನ್ ಓಮ್ಸ್ ಅವರು ಕೊಟ್ಟಂತ ಓಮ್ಸ್ ಲಾವನ್ನು ನೋಡಬೇಕಾಗ್ತದೆ. ಓಮ್ಸ್ ಲಾ ಏನು ಹೇಳ್ತಿದೆ? ಓಮ್ಸ್ ಲಾವನ್ನು ನಾವು ಕಲಿಯುವ ಮೊದಲು ನಮಗೆ ವೋಲ್ಟೇಜ್ ಅಥವಾ ಪೊಟೆನ್ಷಿಯಲ್ ಡಿಫರೆನ್ಸ್ ಇದರ ಬಗ್ಗೆ ನಾವು ತಿಳ್ಕೊಳ್ಬೇಕಾಗ್ತದೆ. ಪೊಟೆನ್ಷಿಯಲ್ ಡಿಫರೆನ್ಸ್ ಅಂದ್ರೆ ಏನು? ಒಂದು ಕಡೆ ಒಂದು 100 ಚಾರ್ಜಸ್ ಇದ್ರೆ ಇನ್ನೊಂದು ಕಡೆ 150 ಚಾರ್ಜಸ್ ಇದ್ರೆ ಪೊಟೆನ್ಷಿಯಲ್ ಡಿಫರೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದ 2 ಪಾಯಿಂಟ್ಸ್. ಇದು ವಿಭವಾಂತರ ಅಂತ ಕನ್ನಡದಲ್ಲಿ ಕರೀತೇವೆ, ಪೊಟೆನ್ಷಿಯಲ್ ಡಿಫರೆನ್ಸ್. ಅದೇ ರೀತಿ ಕರೆಂಟ್ಗೆ ನಾವು ಪ್ರವಾಹ, ವಿದ್ಯುತ್ ಪ್ರವಾಹ, ಕರೆಂಟ್ ಐ ಅನ್ನು ರೆಪ್ರೆಸೆಂಟ್ ಮಾಡ್ತೇವೆ. ಆದರೆ ಈ ವಿಭವಾಂತರ ಮತ್ತೆ ಕರೆಂಟ್ಗೆ ಇರುವಂತಹ ಸಂಬಂಧವನ್ನು ಓಮ್ಸ್ ಲಾ ತಿಳಿಸಿದೆ. ಅದೇನು ಹೇಳ್ತದೆ? ಇನ್ ಗುಡ್ ಕಂಡಕ್ಟರ್, ನೆನ್ಪಿಟ್ಕೊಳ್ಬೇಕು, ಇದು ಕಂಡಕ್ಟರ್ಸ್ ಮಾತ್ರ ಅಪ್ಲೈ ಆಗುವಂಥದ್ದು. ಇನ್ ಎ ಗುಡ್ ಕಂಡಕ್ಟರ್ ವೋಲ್ಟೇಜ್ ಅಂದ್ರೆ ವಿಭವಾಂತರ is proportional to the current. In a good conductor, to talk about two ends of the conductor, voltage is always directly proportional to the current. And this proportionality constant is called the resistance R. Therefore, V is equal to Ri. You can see there, V is equal to Ri is the simplest form of Ohm's law. ಈಗ R ಅನ್ನು ನಾವು ರೆಸಿಸ್ಟೆನ್ಸ್ ಅಂತ ಕರೀತೇವೆ, ಅದರ SI ಯೂನಿಟ್ಸ್ ಓಮ್. ಅದೇ ರೀತಿ ವೋಲ್ಟೇಜ್ ಇದ್ದು SI ಯೂನಿಟ್ ವೋಲ್ಟ್, ಅದೇ ರೀತಿ ಕರೆಂಟ್ ಇದ್ದು SI ಯೂನಿಟ್ ಆಂಪಿಯರ್. ಆಂಪಿಯರ್ ಕ್ಯಾಪಿಟಲ್ ಎ ಅಂತ ಬರೀತೇವೆ, ವೋಲ್ಟ್ಗೆ ಕ್ಯಾಪಿಟಲ್ ವಿ ಅಂತ ಬರೀತೇವೆ. Therefore, voltage, resistance and current are related with the simplest form, that is called Ohm's law. ಅದಕ್ಕೆ ನಾವು ಓಮ್ಸ್ ಲಾ ಅಂತ ಕರೀತೇವೆ. ಈಗ ಈ ಯಾವ ರೀತಿಯ ವೈರ್ ಅಲ್ಲಿ ಏನು ವ್ಯತ್ಯಾಸ ಮಾಡ್ತದೆ ಎಂಬುದನ್ನು ನಾವು ತಿಳ್ಕೊಳ್ಬೇಕಾಗ್ತದೆ. ಅದಕ್ಕೆ ಕೆಲವು ಉದಾಹರಣೆಯನ್ನು ನೋಡ್ತಾ. ಈಗ ನೋಡಿ, ಇನ್ನೊಂದು ನಾನು ವೈರ್ನ ಬದಲಿಗೆ, ಯಾಕಂದ್ರೆ ನಾವು ವೈರ್ ಅಂತ ಹೇಳಿದ ಕೂಡಲೇ ನಾವು ಸಿಲಿಂಡ್ರಿಕಲ್ ಪಿಕ್ಚರ್ ಅನ್ನು ಮನಸ್ಸಿಗೆ ಕೊಡ್ತೇವೆ. ಇಟ್ ನಾಟ್ ಬಿ, ಇಟ್ ಕ್ಯಾನ್ ಬಿ ಆಫ್ ಎನಿ ಶೇಪ್. ಈಗ ನಾವು ರೆಕ್ಟಾಂಗ್ಯುಲರ್ ಟೈಪ್ ಒಂದು ವೈರ್ ಅನ್ನು ತೋರಿಸಿದ್ದೇವೆ ಇಲ್ಲಿ. ಫಸ್ಟ್ ಎಕ್ಸಾಂಪಲ್, say that A is the cross sectional area. You can see here, this is the cross sectional area and it has got length L. Suppose you have maintained a potential difference between the two ends, capital V, then if the current is flowing is I, then resistance of that wire or rectangular piece of conductor is given by V by I. ಅದೇ ರೀತಿ ಅಂತಹ ಎರಡು ಒಂದೇ ಲೆಕ್ಕ ಇರುವಂತಹ ತುಂಡುಗಳನ್ನು ವೈರ್ಗಳನ್ನು ಜೋಡಿಸಿದ್ರೆ ಲೆಂತ್ ಡಬಲ್ ಆಗ್ತದೆ. ನೋಡ್ಬೋದು ನೀವು, ಲೆಂತ್ ಡಬಲ್ ಆಗ್ತದೆ, ಏರಿಯಾ ಕ್ರಾಸ್ ಸೆಕ್ಷನ್ ಸೇಮ್ ಇರ್ತದೆ. ಸೇಮ್ ಕರೆಂಟ್ ವಿಲ್ ಫ್ಲೋ, ದಟ್ ಯು ನೋ, ಬಿಕಾಸ್ the same wire connected one another. Therefore, the current is same, whereas potential difference between these 2 points is V. Next 2 points is also V. Therefore, potential difference is treated as 2 times V. Therefore, what will happen to resistance? Resistance is equal to 2V divided by I. V by I andre R. Therefore, we can call it as 2R. The length double ಆದರೆ resistance double ಆಗ್ತದೆ ಅಂತ ತಿಳಿಸಿದೆ. ಅದೇ ರೀತಿ ನಾವು ನೋಡಿ, ಕ್ರಾಸ್ ಸೆಕ್ಷನಲ್ ಏರಿಯಾ ಎ ಇದ್ದನ್ನು ನಾವೇನ್ ಮಾಡ್ತೇವೆ ಅಂದ್ರೆ ಎರಡು ಶೀಲ್ಡ್ಗಳಾಗಿ ಮಾಡಿ A/2 A/2, ದಿಸ್ ಇಸ್ A/2, ದಿಸ್ ಇಸ್ ಆಲ್ಸೋ A/2, ಲೆಂತ್ ರಿಮೈನ್ ಸೇಮ್. ಈ ರೀತಿ ಮಾಡಿ ಸೇಮ್ ಕರೆಂಟ್ ಅನ್ನು ಕಳಿಸಿದ್ರೆ ಏನಾಗ್ತದೆ? ಪೊಟೆನ್ಷಿಯಲ್ ಡಿಫರೆನ್ಸ್ ಸೇಮ್, ಯಾಕೆಂದ್ರೆ ಇಲ್ಲಿ ಲೆಂತ್ ರಿಮೈನ್ಸ್ ಸೇಮ್, whereas the cross sectional area is divided by 2. ಕರೆಂಟ್ ಫ್ಲೋ ಆಗುವಂಥದ್ದು I/2 ಆಗುತ್ತೆ. ಅದ ಕಾರಣ once again this 2 will go to the numerator. R is equal to V by I/2, that is equal to 2R. ಇದರ ಅರ್ಥ, ನಾವು ಒಂದು ಕಂಡಕ್ಟಿಂಗ್ ವೈರ್ ಅನ್ನು ಎರಡು ಶೀಲ್ಡ್ಗಳಾಗಿ ಮಾಡಿದ್ರೆ ಅದರ ರೆಸಿಸ್ಟೆನ್ಸ್ ಡಬಲ್ ಆಗ್ತದೆ. In general, what we are trying to say here is the resistance of a conductor is not directly depending on the length of the cross-sectional area. Therefore, what it depends. Now, very important, this relation should be knowing. Resistance is proportional to length and inversely proportional to the area cross section, but with the constant of proportionality, that is called resistivity. Rho ಅಂತ ಹೇಳ್ತೇವೆ. Rho is resistivity. ನೆನಪಿಟ್ಕೊಳ್ಬೇಕು, length is measured in terms of meter, area cross section is measured in terms of square meter square, and if you rearrange this, rho is equal to say, always remember this, rho is equal to R into A, sorry, R into A into R divided by L. Therefore, you remember, just rearrangement, rho into L. Then you see that resistance as the unit of ohm you write like meter square divided by meter will remain. Ohm meter is the unit of resistivity. Ohm meter is the SI unit of resistivity. This is very, very important. Resistance is equal to rho into L by A, or resistivity is equal to AR divided by L. That means measured in terms of ohm and meter, ohm meter. Very, very important point to be remembered. Therefore, resistivity of the material will decide whether it is the material is a conductor or semiconductor or a superconductor or something like that. Okay, that's very important. Now you see, once again, we'll go to some new ideas which you have not studied earlier. Suppose you take current per unit area, take a normal to the current. ಈಗ ಒಂದು ವೈರ್ ಇದ್ರೆ ಈ ರೀತಿ ಒಂದು ವೈರ್ ಇದೆ. Is a wire. I'm talking about an area which is normal to the flow of current. Current is flowing like this in this wire. Then area of cross section is A. Okay, area of cross section is A. Then I is the current. You have potential difference of V. Potential difference between these two ends is V. Then current, we define a term called current density. Current density. What is that? I by A is called current density and denoted by J. Illi, electric field is always a vector. Many times we forget to write the symbol of vector. Current density is also a vector. Vector means for that letter symbol you have to put a arrow mark on the head. This is very important. People will forget to write. The textbook ಅಲ್ಲಿ ನೀವು ನೋಡಿದ್ರೆ ಅದು ಕ್ಯಾಪಿಟಲ್ ಲೆಟರ್ ಆಗಿ ದಪ್ಪದಲ್ಲಿ ತೋರಿಸ್ತಾ ಇರ್ತಾರೆ. ಅದ ಕಾರಣ ಅವರು ಸಪರೇಟ್ ಆಗಿ ಇದನ್ನು ಬರೆಯುವುದಿಲ್ಲ. ಯಾವುದನ್ನು ನಮ್ಮ ಆರೋ ಮಾರ್ಕ್ ಬರೆಯುವುದಿಲ್ಲ. ಅದರ ಅರ್ಥ ಆರೋ ಮಾರ್ಕ್ ಇಲ್ಲ ಅಂತ ಅಲ್ಲ. ಅದಕ್ಕೆ ನೆನ್ಪಿಟ್ಕೊಳ್ಬೇಕು. ಇ ಇಸ್ ವೆಕ್ಟರ್, ಕೆ ಇಸ್ ಆಲ್ಸೋ ವೆಕ್ಟರ್, ಇ ಇಸ್ ಎ ವೆಕ್ಟರ್. ಈ ಎಲ್ ಎರಡು ಕಡೆ ಕ್ಯಾನ್ಸಲ್ ಆದ ಕಾರಣ ಓಕೆ ವಿ ಹ್ಯಾವ್ J, E is equal to J into rho, or J is equal to sigma into E. Sigma is nothing but conductivity. Sigma is called conductivity. Conductivity. Rho is called resistivity. Resistivity and conductivity. Resistivity and conductivity. They are reciprocal to each other. Sigma is equal to 1 by rho, or rho is equal to 1 by sigma. Therefore, we have a definition for current density J is equal to sigma into E. This is very, very important. Again, E is equal to J into rho, or J is equal to sigma into rho. If you rearrange that, you can get it that. So that is called current density. That is a very important point to be remembered. Okay. Next, we will go to a topic called drift velocity. What is drift velocity? See, what is very important here is when in any conductor, when you before applying any electric field, you see that electrons are moving randomly in the conductor. They are moving randomly. Suppose there is sufficient space inside. Suppose you think of thick wire, for example. They keep on moving randomly at different directions. Like that. They can simply move like randomly like this. Different directions they can move. Suppose this is the initial point, the final point. They will simply keep on jumping around like this, get bounced back because of different obstacles in between. Then they reach here. Now, what I am saying is, if there are n number of particles, suppose there are n number of particles, that means electrons, each one is moving with the velocity vi. Let us say each one is moving with velocity small letter vi. This is the velocity of electron, and there are n number of such electrons. Then you see that 1 by n summation, I take summation of all I equal to 1 to n, all of them I take, then Vi is equal to 0. What does it mean? Net velocity is 0. Net velocity 0 means what? If there are 10 moving in one direction, another 10 will be moving in the opposite direction. Therefore, in general, we say mathematically, average velocity of electrons is supposed to be 0. ಇದು ಯಾವಾಗ ಅಂದ್ರೆ when there is no applied electric field, potential difference is not applied. Now what will happen if we apply the potential difference? Potential difference if we apply, or if we apply an electric field on the conductor, then all these electrons get accelerated. What is the acceleration? Suppose you say E is the potential difference. Let us say E is the potential difference. E is the potential, sorry. Right somewhere here. E is the electric field applied. Then the acceleration achieved by the electron A is equal to minus E into E divided by M, where M is the mass of the electron, E is the electric charge, capital E is the electric field. This is very important. Each electron is get accelerated by the amount EE divided by M. Acceleration denoted by small letter A, electric field is E. Now, if I go like this, suppose I think of each electron, I catch each electron, any ith electron, and I apply electric field before and after, and rearrange the thing. What will happen? What will happen to their behavior is very important. And I want to know the total effect of electric field on the entire group of electrons. That is very important point to be remembered. Therefore, what I see here, very important here, is instead of taking different time intervals, what is observable according to the free electron theory is after each successive bombardment or collision, electrons will take rest. That time is referred as a relaxation time, tau. Relaxation time, tau. Relaxation time. Relaxation time. And we see that this, although net velocity of this electrons is 0, we see that effectively all electrons are drifted by a factor called drift velocity. Drift velocity is given by minus E divided by M into tau. Okay, this is called drift velocity, where tau is referred as the relaxation time. Here V is referred as the drift velocity. It is nothing but the acceleration. If you rearrange, you get the term which is the drift velocity, where EE divided by M into tau. Now, therefore, tau is not the time. Therefore, drift velocity does not depending on the time interval, whereas drift velocity depends on electric field and the relaxation time of the electrons which are in random motion. This point to be also remembered. Now again, once I know the relaxation time, I can get one more important parameter called the density, that is the charge density J, or current density J, also can be written in terms of N E square divided by M into tau into E. N E square divided by M tau into E. Current density J. This is also very important relation. Now N is the total number of electrons which are moving. E is the charge. M is the mass of this electron. Tau is the relaxation time. E is the electric field. And if I write it in terms of sigma, that is the conductivity sigma, then it will be N E square tau divided by M. N E square tau divided by M. This is also important relation. Sigma is conductivity, electrical conductivity. Sigma is N E square tau divided by M. So people have to remember, student has to be remembered these two important relations. How this derived is not so important because it all come from the free electron theory. and which has got a tedious steps to be derived. It's not essential for you. Whereas the relationships are important because in any competitive examinations, you can expect the question based on the sigma relation as well as J relation. Therefore, J is equal to Ne square divided by M tau into E. Similarly, conductivity is sigma N E square tau divided by M. This is tau, remember, this is tau. And conductivity depends on what now? Conductivity depends on number of electrons participating and relaxation time, electric charge and mass. This, I hope this point you are able to remember. That talks about drift velocity. In the textbooks also you see one or two problems, so that you can solve those problems. It will give an idea of how conductivity is measured or how can be calculated or estimated for a given current conductor, current carrying conductor. Okay. Further we'll go to one more definition called mobility. What do you mean by mobile? Say mobile means moving in general. Therefore, whenever conductivity, a term like conductivity you come across, you see that the charges are moved from one term to one end to the other end. That is called mobile charge carriers. Therefore, we define this mobility mu. Mobility is defined as mu. Mu is equal to Vd, magnitude of drift velocity, divided by electric field. Magnitude of drift velocity divided by electric field. Why I say magnitude of the drift velocity? Because mobility we are not taking as a vector, we are taking as a scalar. Therefore, mobility is Vd divided by E. Therefore, magnitude of drift velocity per unit electric field. Magnitude of drift velocity per unit electric field will give you mobility. Therefore, once I know mobility, what is the SI unit? SI unit of mobility will be, that's also important, one of my question. SI unit will be meter square per velocity, volt into second. This point also remember. Meter square voltage into second. And it is always remember, it is measured in terms of 10 to the power 4. The units of 10 to the power 4 is because it is in the order of 10 to the power 4 practical unit. Therefore, in general, centimeter square per velocity second also used in some cases. And if you know Vd, because we already written Vd is equal to E tau E divided by M, then from this I can write expression for mobility also. Therefore, mobility if I take, that will be Vd divided by E. Vd divided by E, that is E tau divided by M. E tau divided by M. This also you can remember because tau is always talks about average collision time, or is also referred as the relaxation time. Tau is also called as average collision time. Average collision time. Average collision time. Because we assume that electrons keep colliding from one point to another point as they move because of various factors like impurities, similarly lattice points, even some hindrances on the way of the electrons will lead to the mobility or the resistivity, which will lead to the collision of the electron. Therefore, resistivity basically because one of the factor is here the collision of the electrons to various hindrances on the way. Okay. Therefore, after defining Ohm's law, we have defined terms like drift velocity and other things. Now, we'll go to understand what are the difficulties with Ohm's law. For that, we go to what are the limitations of Ohm's law. That is very important. Limitations of Ohm's law. when I talk about limitations of Ohm's law, limitations of Ohm's law. Now, I already mentioned you, Ohm's law is applicable for the conductors only. Ohm's law is applicable to conductors only. Now, what are limitations? Say, you know, if you think of any good conductor, if I plot a voltage versus current curve, this voltage versus current, it is always linear. It's always linear. This is the proper Ohm's law. This is for a conductor. For a conductor. Whether this is true for other material, it is not true for other material. Remember, this is true for a conductor at a given temperature. At a given temperature, that is true. If temperature varies, if the size of the conductor varies, then that Ohm's law you cannot simply apply to another conductor. For a given conductor at a given temperature, the Ohm's law is valid. But what happens? Suppose you think of a semiconductor. For example, semiconductor diode characteristics you studied. If I think of the diode characteristics, the current versus voltage, if I plot it, it is always a curve like this, right? Therefore, what? It is not linear curve. It is not linear curve. Therefore, we say for a semiconductor, Ohm's law is not valid. Ohm's law is not valid for semiconductor. If you think of a material like gallium arsenide, for example, then if I plot the current versus voltage curve for gallium arsenide, you find that a curve of this kind. That means for gallium arsenide, it is not valid. Ohm's law is not valid. This point you remember. Ohm's law is valid for a good conductor, for a given conductor, and at a given temperature. That means resistivity depends on some other factors. What are the factors on resistivity depends? That we see. Therefore, we have to see how the resistance changes with the not stored. I written PPT. Okay, anyway. Let us see. Now, if you think of resistivity, what is the order of resistivity for a given good conductor? You know that resistivity of metals, resistivity of the metals, resistivity of metals is of the order of 10 to the power of -8 ohm centimeter to 10 to the power of -6 ohm meter. That is the order of resistivity of a metal. And from this point, you remember, for conductor, resistivity is much less. You see 10 to the power -8 ohm meter. For insulator, resistivity is more. For semiconductors, the value lies between the two. Therefore, this point you remember. Now, how the temperature dependent resistivity can be studied. For understanding that, we should know how the temperature dependent resistivity for different materials. Now, if I generalize this for a metallic conductor, resistivity, the resistivity at a given temperature T is given by resistivity at one particular temperature rho naught into 1 plus alpha into T minus T naught. So you remember here, rho T is the resistivity at temperature T, rho naught is the resistivity at a given temperature. Alpha is called coefficient of resistivity, that is temperature coefficient of resistivity. Temperature coefficient of resistivity. Temperature coefficient of resistivity. And T is the temperature T, as I told you, T naught is the temperature at a particular value. And this is T is here, remember, T is always here measured in terms of centigrade. That point you have to remember. C is measured in terms of temperature, and alpha is positive for metals. Alpha is positive for metal. This point also you have to remember. Alpha is positive for metals. This is another important point to be understood. Now, therefore, I am saying in general, if you think of resistivity of a copper resistivity of a copper at a given temperature, let us say at low temperature, I go for a low temperature, T I measure in terms of Kelvin here, Kelvin, then resistivity in the y-axis for copper, you see that it varies like this in the case of a copper. Similarly, if you think of a good conductor, there is a nichrome wire, for example, nichrome wire, then resistivity will be like this. Rho versus temperature, Kelvin. That means at 0 Kelvin, resistivity is not 0. It is having certain value. Similarly, for semiconductor, if you plot the resistivity versus temperature, then you find that it decreases with the increasing temperature. Resistivity decreases. In the case of semiconductor, for example, it may be, you think of any semiconductor like germanium, for example, here. This is a wire, it is a metal, okay, metal wire in general, mixed metal. Nichrome wire, for example, nichrome wire. It is made up of nickel, chromium, and zinc. Therefore, if you think of this, you see the variation of resistivity for different materials at different temperatures. It is linear increasing like this, exponential increasing in the first case. Second case, not having a zero value, is having a higher value at even 0 Kelvin. That is called nichrome wire. And germanium like semiconductor, it decreases with the temperature. This is the point to be remembered in the case of temperature dependent resistivity. And this is very important parameter. You know that if resistivity of a material becomes 0, then abruptly later, if you study in the higher classes, that material becomes superconductor. This is also important point to be remembered. How to relate the resistivity and temperature variations? For that, in your textbook, you find a lot of problems. Simplest problems you can study, which will give you a very clear idea of how you can measure the resistivity for different materials. Okay. Let us see. For example, if you have a problem of like this, one problem I try to solve very, very quickly. You have a platinum wire of resistance which is kept kept on ice. Kept on ice. Remember, it gives a clue. Kept on ice means temperature is 0 degree centigrade, and we found that resistance is found to be 5 ohm. Then at the other end, it is kept at steam. Resistance is 5.23 ohm. Therefore, this is 0 degree centigrade ice. Steam means 100 degrees centigrade. This is ice. Then, when thermometer is inserted in hot bath, resistance of the platinum wire is found to be 5.795 ohm. 5.795 ohm. Therefore, you have a platinum wire, resistance at one point is 5 ohm, other end it is 5.23. When thermometer inserted in a hot bath, the resistance of the platinum wire is 5.795 ohm. Calculate the temperature of the bath. So this is very simplest problem is possible to understand this. Say you have R naught, resistance at 0, 5 ohm, R 100 degree, resistance 100 degrees, 5.23 ohm, resistance at a given temperature RT general 5.795 ohm. What you have to do? You have to calculate temperature. Temperature is given by RT minus R naught divided by R100 minus R naught into 100. Because RT, you know, formula RT is equal to R naught into 1 plus alpha. Just rearrange this, you get this. Rearrange this, you will be getting this. If you substitute all the required values, you find that 345.65 degrees centigrade. This problem is worked out in the textbook. Please go through and work it out by substituting the values so that you get an idea of how a resistivity, with the help of resistivity, temperature can be calculated, or resistance in terms of or resistance is given, temperature can be calculated, even otherwise can be also done. Every time you find a problem on this in your competitive examination, which will be useful for you if you practice it well. Okay. Next, once I know the properties of this electric current, then where they are useful? They are useful in our day-to-day appliances, like say various electrical instruments, either it is maybe electric bulb. Nowadays we use LED bulb, otherwise incandescent bulbs are used, then fans are used, electric geysers are used, iron box is used. In all those instruments, this electric appliances, we make use of the properties of this current. Therefore, we have to study these things. One such property is calculation of electrical energy. Electrical energy. Then we always calculate what is the power consumed. What is electrical energy? When I say when the current is flowing in a conductor, then potential difference is applied between the two ends. Then there is always a potential difference. Say potential at one end VA, potential at the other end VB. Then either VA is greater than VB or otherwise. You know that there is a potential difference. Whenever we say potential difference, or you say in general VA, difference VB is always greater than 0 because it is at a different potential. Difference is always some value which is greater than 0. Therefore, and if this current is flowing for a time interval of delta t, let us say delta q is the amount of charges flowing, and delta t is the time interval of flow, then what is very important for us to note is how these are related. Then I say always, the U definition delta Q by delta T will give you the current, right? Gives you current always. Or in other words, delta Q into is equal to delta T into IR. So you can write. Therefore, there is a change in potential energy. That is very important. Change in potential energy. There is a change in potential energy. What is the change in potential energy? The change in potential energy can be written as delta Q into potential at one point. Let us say potential at A is less than the potential at B. Therefore, VB minus A, then I write it as delta Q into V, some value V, delta Q into V. Now, if it can be taken as a positive or negative depending on which is greater and which is smaller. And therefore, change in potential energy, if I write delta Q, delta of U, potential energy, change of potential energy, delta U, that is initial or final energy, right? Final potential energy minus initial potential energy, that you can calculate, then you can find it I into del V into delta P, which is greater than 0, or if you put a minus sign, it will be less than 0. Therefore, you remember here, when charges move from one end to the other end due to the collisions, the kinetic energy in them will lead to change in the total energy. As a result, some energy factor comes into picture. That is called delta K, because you know that energy cannot be created or neither destroyed. As a result, you can call it as delta K, conservation of potential energy in general. Delta K is equal to minus delta into U potential, which you calculated, minus delta U potential. Now, if I say if it is greater than 0, if this is, that is I into V into delta T is greater than 0, then delta K can be constructive use. That means some work can be done with the help of that kind of changes taking place in the system. Now this can be converted in terms of energy dissipated. Energy dissipated per unit. Energy dissipated per unit time is nothing but the power dissipated. P we call power. That is delta W by delta T. Delta W is nothing but the work done. Or in general, P can be written in terms of V into I. For potential difference, V into I. Therefore, V energy dissipated is nothing but the power. This we call it as power. Some work is done, and because of that work, some kind of some changes in the energy taking place, which resulted into work that can be measured in terms of power or called power. P is equal to V into I. This P is equal to Vi also can be written, because you know V is equal to R into I. This can be written as I square into R, because P is equal to V I into R, I square into R. P is equal to I square into R is another expression for representing the power. Power consumed, what do we say? Power consumed or the work done. Or you can write in terms of V square by R also. P is equal to, if you write V square divided by R, also you can write. Same thing you can write in terms of V and R. Therefore, that is very important. Therefore, we can generate some kind of work, or we can make use of this flow of charges in wire, which can be converted into effective work. That is called potential or the power delivered or power consumed. Now you see that in particularly electrolysis process, that is, you have a anode and your cathode, you have a solvent in which you pass the current, then you see that electrolysis taking place. This also a kind of doing work. This is done in our very earlier days. Therefore, now where you find this potential difference? There is a question. Where you find the potential difference? How we can store energy in the form of this energy you want to store? How do you store it? Therefore, we have very important things like cells. Cell. Now, what is a cell? Or in general, combination of the regular term we use battery, where more than one cell is connected together, either series or parallel. Then these are called cells, or in general, they are generating EMF, electromotive force. Electromotive force, EMF. Therefore, they maintain steady current. In a cell, they try to maintain a steady current. What are the things you have in a cell? You have an electrode, two electrodes. One is called cathode, other one is called anode. In between, some electrolyte will be there. And So you have electrolytes we call, one is positive, P we say positive, other one is negative, P or N, P side or N side. In general, okay, in general, we write them as positive and negative, and in between, say these are two electrodes, and they are immersed in a electrolyte. Some electrolyte is there. Sometimes in liquid form, sometimes in solid form. Electrolyte. Electrolyte is available. And if you connect these two ends externally, these two ends is connect externally using some wire to some bulb like such, some resistance, then you see that there's a closed circuit, and EMF will be flowing with EMF, because electrolysis takes place. As a result, some current will flow from I, that is from positive to negative side, some current will flow. This is referred as a cell, because you require electrolyte solution, and the two electrodes, these two are electrodes, these are electrodes. Electrodes are dipped in electrolyte solution. So in like the various chemical cells you come across in your school, where you make use of this property of this one, what I say, electrolysis process, and you see that potential difference at the two are not same. Therefore, we say epsilon or E. Now you can call it E or small letter E, epsilon also is called. Then potential difference at one end plus potential difference at the other end is always greater than 0. Effective potential difference, we write the potential difference between P and N is always, sum if you take, it will be greater than 0. This is called EMF, electromotive force. Therefore, if you remember, this E is not a force, but it is a potential difference. It's a potential difference. Although we call it as electromotive force, this is nothing but a potential difference. And once I have a potential difference, then I can study the characteristics of the various cells. Therefore, you think of V is a potential difference at one end, V plus, V minus is the potential difference at the other end. Then E is the EMF of the cell, we call EMF of the cell. That is, this EMF is always referring to an open circuit. That means when the cell, the two electrodes are not connected to an external circuitry, then it is called an open circuit. Once you connect it to an external bulb like a structure or a resistance, then it is called a closed circuit. Therefore, the potential difference V, if I say potential difference is V, then is always V plus V minus, then I into R. R is the internal resistance. Of the materials used in the electrolyte. Therefore, in general, V, if I write, that is equal to epsilon EMF E minus I into R. E, epsilon also equal, looks like epsilon, therefore E minus IR. The potential difference V is equal to E minus IR. This is very important to remember. Potential difference is V. When I say potential difference between the P and N, positive and negative electrolyte in the open circuit, that is E is equal to I into R. Now also we see that potential difference is always I into R. Therefore, suppose I say potential difference is I into R, then Ohm's law, I into R, that is epsilon minus I into R. This can be, from this you can write I is equal to EMF E divided by R plus R, rearrange that and you get it. I is equal to E divided by R plus R. For in general, this is EMF of a cell in which the current flowing can be calculated using E divided by R plus R. So remember, maximum current that can flow only when R, capital R is equal to 0. It doesn't show any resistance. Whereas internal resistance cannot be avoided. It always remains in any electrolyte internal resistance ring. Therefore, I think we are able to cover only part of the topic. In some other time, I'll continue with the second session because it is a very large, topic. If you have any doubts, you can please ask right now. Will other possibilities of combinations will check in the next class. Are you there? Anybody? Hello?
Sir, namaste.
Namaste, namaste.
So end of the session, sir.
I could not cover the entire topic because it's a big topic. I have done it 50% almost. Yes, sir.
ಎಷ್ಟು ಕ್ಲಾಸ್ ಆಗ್ಬೋದು ಸರ್? ನೆಕ್ಸ್ಟ್ ಬೇಕಾದ್ರೆ ಅದನ್ನ ಕಂಟಿನ್ಯೂ ಮಾಡ್ಕೊಳ್ಳೋಣ ಸರ್.
ಇನ್ನೊಂದು ಕ್ಲಾಸ್ ಸಾಕಾಗಬಹುದು ಸರ್. ಇನ್ನೊಂದು ಕ್ಲಾಸ್ ಅಲ್ಲಿ
ಓಕೆ ಸರ್, ನಾನು ನೆಕ್ಸ್ಟ್ ಡೇಟ್ ಹೇಳ್ತೀನಿ ಸರ್ ನಮಗೆ.
ವೆರಿ ಬಿಗ್ ಟಾಪಿಕ್ ಅಲ್ವಾ, ಎಲ್ಲವನ್ನು ಕವರ್ ಮಾಡ್ಲಿಕ್ಕೆ ಆಗಲ್ಲ.
ಓಕೆ ಸರ್, ನಾನು ನಿಮಗೆ 16th ಆನ್ವರ್ಡ್ಸ್ ನಿಮಗೆ ಇಂಟಿಮೇಟ್ ಮಾಡ್ತೀನಿ ಸರ್.
ಎಸ್ ಎಸ್ ಶೂರ್.
ಆ ವೀಕಲ್ಲಿ ಯಾವ್ದಾರ ಒಂದು ಡೇಟ್ ತಗೊಂಡ್ರೆ ಇದು ಕಂಪ್ಲೀಟ್ ಆದಂಗೆ ಆಗುತ್ತೆ.
ಓಕೆ ಓಕೆ ಓಕೆ.
ಸೊ ಚಾಟ್ ಬಾಕ್ಸ್ ಯಾವ್ದು ಕ್ವಶನ್ಸ್ ಇಲ್ಲ ಸರ್, ಏನಾದ್ರು ಕಳಿಸಿದ್ರೆ ನಾನು ನಿಮಗೆ ಇಮೇಲ್ ಮುಖಾಂತರ ತಮಗೆ ಕಳಿಸ್ಕೊಡ್ತೀನಿ ಸರ್.
ಶೂರ್ ಶೂರ್ ಶೂರ್.
ಸೊ ಎನಿವೆ, ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಥ್ಯಾಂಕ್ ಯು.
So today's delivering the talk is very informative and insightful talk on today's topic. ಭಾರಿ ಸರಳವಾಗಿ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ಹಲವಾರು ಎಕ್ಸಾಂಪಲ್ ಉದಾಹರಣೆಗಳ ಮೂಲಕ ವಿದ್ಯಾರ್ಥಿಗಳಿಗೆ ತಿಳಿಸ್ಕೊಟ್ಟಿದ್ದೀರಾ. ಸೊ on behalf of KSTA and myself, once again thank you sir. ಸೊ ಇಂದು ಹಾಜರಾಗಿದ್ದ ನನ್ನ ಎಲ್ಲ ವಿದ್ಯಾರ್ಥಿಗಳು, ಅಧ್ಯಾಪಕರು, ಶಿಕ್ಷಕರು ಹಾಗೂ ನನ್ನ ಸಹೋದ್ಯೋಗಿಗಳಿಗೂ ಕೂಡ ಧನ್ಯವಾದಗಳನ್ನು ತಿಳಿಸುತ್ತಾ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ಸೊ ಎಂದಿನಂತೆ ನಾಳಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದಲ್ಲಿ ಸುಮಾ ಮೇಡಮ್ ರವರು ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು, ನಾಳಿನ ತರಗತಿಯಲ್ಲಿ ಇಂದಿನಂತೆ ಹೆಚ್ಚಿನ ವಿದ್ಯಾರ್ಥಿಗಳು ಹಾಜರಾಗಿ ಆ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಕೇಳಬೇಕೆಂದು ನಮ್ಮ ವಿಜ್ಞಾನ ಮತ್ತು ತಂತ್ರಜ್ಞಾನ ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ಮತ್ತೊಮ್ಮೆ ತಮ್ಮೆಲ್ಲರಿಗೂ ತಿಳಿಸುತ್ತಾ ಈ ಒಂದು ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮವನ್ನು ಮುಗಿಸುತ್ತಿದ್ದೇವೆ. ಎಲ್ಲರಿಗೂ ಧನ್ಯವಾದಗಳು. ಒನ್ಸ್ ಅಗೇನ್ ಥ್ಯಾಂಕ್ ಯು ಸರ್.